Okay, this is going to be the second example with the trig substitution. Again, very complicated problems. So keeping in mind that we have our 1 minus sine squared, tan squared plus 1, and secant squared minus 1, right? Which one does this look like? Well, there's only one of them that has a plus in it. So not that one, not that one. Now, this time we're going to be a little more sophisticated. I know that I need to pick tan theta. I also know that if I put a 1 here, it's going to screw me over. So as I said to you, when there's a number that isn't a 1 with it, if I give you x squared plus 1, I just handed you a very nice gift because these are a lot easier when there's no numbers there. So, but it has to be a perfect square. So you take the square root of 9, which is 3. You put it there. Now, I have to replace a dx. Again, I wrote the dx on the top of the fraction for you for your convenience. So you're going to replace that dx with the derivative. So the derivative of tan is our buddy secant squared. And remember, we're changing variables. We cannot use x anymore. We have to use theta. Okay, so the derivative of tan is secant squared. And there's a 3. So the 3 is a constant, just goes along for the ride. Now, I'm going to make my trig substitution. That's the whole point of doing this. You're making a trig substitution. So I'm going to keep that 3 up there. Where the dx is, I'm going to put this. Be very careful when you do this, because if you screw up this step, the problem is over. Whoops, I already fucked up the step. D theta, sorry. I forgot that the derivative, you got to put the derivative. These are derivatives. There should be a d there. I realized it when I got here, and I went and fixed it, and you never knew. So you could do that to me, and I'll never know that you forgot it until you got here. You want to make sure, remember, these are derivatives, and you're going to find an antiderivative, so you want to write that there. It's just bad form if you don't. So now where x is, over here, I'm going to put, right, replace x with 3 tan theta. And yes, I'm very tempted to put t there, but I won't. I'm going to do this properly. And you need to do it properly. Same thing here. I'm going to put 3 tan theta. I'm going to square it plus 9. Now, this is where I must absolutely 100% do this on the side. Just for convenience here, I am going to write t. All right, I have to simplify this radical. I need to simplify this whole thing, but I start by doing this one. So I'm going to do it on the side. So when I square that, I get 9 tan squared theta plus 9. I'm going to factor out the 9. Right? You have a 9 here and a 9 here. GCF, you factor it out. So you're left with tan squared. I didn't leave myself enough room. Right? That 9 goes away, you get tan squared. This 9 goes away, you get plus 1. My voice doesn't want to cooperate with me. So now you replace what tan squared plus 1 is, which is secant squared. Remember, theta, not x theta. Now take square roots. Square root of 9 is 3. Square root of secant squared is secant. Remember the whole point of doing this stupid-ass question. Why you do this. Why do you put trig guys in? To kill the radical. The radical is what F's up this question. This is not a U substitution problem. This is not, if that was U, this is not du, right? The derivative of x squared is not x squared. So you have no choice but to somehow get rid of the x's with something that will let you get rid of the radical. So you do all this on the side. Then you go back to your integral. I'm going to write it all again. 3 and 3 make 9. So on the top, I have secant squared, d theta. On the bottom, I have this squared, which is 9 tan squared theta. This one's going to be a little more nasty. And then that radical, I simplified on the side. And where the little red circle is, I'm going to put 3 secant theta. Now, nice thing, the 9's cross out. Yay. Nothing else crosses out. I mean, the secant will cross out with one of those and leave you with a secant. So, gone. This one's gone. This is still there. This is still there. And that's still there. And, of course, your d theta has to be there. So I'm going to write. So, again, you got something a little complicated here. So I'm going to write and show you. It turns out to not be as bad as it looks. But I'll have to erase all that and rewrite it. You'll never know. Okay, so I erased a lot of the stuff I did, but I left this there on purpose. So I was doing my crossing out. It left me with a secant on top and a d theta on top. It left me with tan squared and a 3 on the bottom. Everything else is gone. So now I'm going to simplify this. Now, again, if you do this in a clever way, this becomes much easier. So what I want to do, you don't try integrating this the way that it is, because it's too ridiculous. You can start putting the trig things that you know in there. So you got to do this. And now I'm going to do it on the side because it gets kind of crazy. Look, you know that secant is 1 over cosine, right? You know that tangent has sines and cosines in it. So you can replace, right? It's 1 over cosine divided by. Now I'm getting rid of this 3. This 3 is in the way. It's annoying me. I'm removing it. I don't need it there, right? I can just put it in the front, just so it's not distracting me when I'm doing this part. So I have 1 over cosine. Now, but tan is sine over cosine. So that's sine squared over cosine squared, right? So it's really 1 over cosine divided by sine squared over cosine squared, right? These involve a lot of work. So you get 1 over cosine, right? Keep, change, flip. Make that multiplication. Flip that over so it's cosine squared, sine squared. You're like, this doesn't help me. It's going to help you. You're going to cross out that, right? Cross out the cosines. So you get cosine over sine squared. And now you're still saying the same thing. This doesn't help me. So that's cosine over sine times sine, right? I'm going to put a little 1 there just for fun. But check this out. You have cosine over sine. Cosine, now tangent is sine over cosine, but cosine over sine is cotangent. And 1 over sine is cusc, our buddy cosecant. So that whole thing simplifies down. Using your trig identities, you're going to get cusc times cot d theta. I do this little simplification. Now, it's possible to do it. It's not, you can't replace tan squared with secant squared plus 1 because it doesn't, if you had something like x over x plus 1, I hope that you guys are not moronic enough that you would cross out these x's. I've seen students do this and it's just ridiculous. This using sines and cosines is probably the most straightforward way to do it. Right? You don't want to try to get too cute with these. Right? So you want to just put everything in terms of sine and cosine, simplify it as much as you can, and pray that it's one of the ones you already know. And the thing is, it is. Right? Once you cross out that extra cosine, right? But this is the key, is understanding that from here you split it up. Knowing what this is. Could you have integrated it there? Yes. You could have done it with cosine and the sine squared on the bottom and used the U substitution with sines and cosines. You don't want to do that. It's right. It's too much. I simplified as much as I could using my trig identities. And now I got it, right? I mean, I know that the derivative of cosecant is negative coscot. Negative. So when I find the antiderivative, I have to put in negative 1/3 cosecant theta plus c, right? That's the antiderivative. The derivative of this, the derivative of cos is coscot with a negative sign. So that's why that negative is there. You're like, yay! They're like, no, boo. I still have to do this thing. I still have to draw my triangle. The tan theta is x over 3. Right? Just divide both sides by 3. So now I'm going to make my triangle. Now remember who tangent goes with. Tangent, right? Toa. Opposite, adjacent. Always put your theta here for convenience. On your cheat sheet that I'm going to make for you, I already have a right triangle there. This is why it was there. You're like, why are we giving this? We never use this stuff. You use this stuff here. Like when you learn this, you were like, when am I ever going to see this again? Like, surprise, it's here. So opposite is x. Adjacent is 3. And the hypotenuse, I have to use the Pythagorean theorem. No, you don't. I told you already, this will always, look, a squared, b squared, c squared. This squared plus this squared is that. So, hello, right? You get x squared plus 9, square root. You just put it right there. Easy peasy, right? Remember, that was opposite. That's adjacent. And come on. I mean, if you don't know the hypotenuse of a right triangle, what the hell are you doing in Calc 2? So, I need to replace cusc. I don't know what cusk is. Exactly, but you know who it goes with. So what you do is you take your triangle and you read off your buddy's sine, because remember, sine and cusk are reciprocals, right? Sine is equal to 1 over cosecant. So you look at the triangle, you read off sine, which is opposite over hypotenuse. That's why you make the triangle. And now to get cusk, I just flip that over, right? You take the reciprocal of that. So the antiderivative of this is going to be 1/3 times, now flip that. The radical x squared plus 9 goes upstairs, which makes sense to me because it's downstairs in the derivative. This is the antiderivative over x plus c. And again, if you want to be nice and make it look pretty, you could take the negative and put it on the top and put radical x squared plus 9. And you could take the 3 and put it with the x on the bottom. You absolutely don't. If you left this answer here, this is perfect. Just making it look nicer. So again, it kind of makes sense. If you take the derivative of that thing, right? Remember, that would be x squared plus 9 to the 1/2 power. If you took that derivative, the power would be negative 1/2, which would move that radical part there. Now, how did you get an x squared? From this thing. You'd probably have to use the quotient rule on that. Good luck with that. But this is why you have an x squared on the bottom. It's not as simple as, the thing would be that. Sorry. It's all stuck written on there, right? It can't be just that. You have to have something else with it or you wouldn't get that x squared there. All right, so you see these examples get very nasty. I can't do them quickly and I can't do them easily. They take a lot of work. You have to pick the appropriate trig substitution, take its derivative, plug it all in, simplify that radical so the radical goes away, cross out whatever you can. Now, I got something pretty complicated here. This was not trivial to do. I had to do this on the side. I had to replace that with sines and cosines, cross it out as much as I could, and then recognize that it was already a derivative of something, right? Cos cot is already a derivative. You want it, they should always work out that way, all right? But you can get some not so nice integrals here. And then again, I got cusk. I don't know what to do with cusk. I know what to do with sine. So I drew my triangle. I figured out sine, flipped it over, got cusk, and then popped it in there. All right. So again, this is always the process, long process, and this is involved. That's why it's called the mother of all the techniques, because you're doing a lot of different things in these problems, and there's so many places you can go wrong. All right. Now the next one I do is actually going to be a lot easier, so I might do 2 in that video. I don't know. That is a long.